contribution comes from Center for Applied Energy Research from University of Kentucky, and is co-authored by Wilfred, Zhang, O'Brien, Bao, and Professor Davis. And the title of the presentation is Fischer-Tropsch Synthesis Comparison of Alkali Metals as Promoters. And the presentation is going to be given by Dr. Yang Qing Zhang. Please.
Thank you, Mr. Chairman. Good morning, everybody. This morning I'm going to give a talk on the activity and the selectivity for Group 1 Alkali-Promoted iron-based catalyst. First, let me thank my co-authors. Mr. Wilfried is a master student from the University of Zhang, France. And Dr. O'Brien is a chemist. He used to be with us, and now he's with Subcommittee Incorporation. And Mr. Shi Bao is a chemist for the center, and all this work are under the supervision of Dr. Bertrand Davis. First, let me spend a minute to introduce our center and the Catalysis Center we have now affiliated with Center for Applied Energy Research, University of Kentucky. We have altogether 18 chemists and chemical engineers and postdoctoral researchers working together. Dr. Bertrand Davis is director for the Catalysis Center, Catalysis Research and Testing Center. What we do is mainly Fischer-Tropsch synthesis studies. We both do cobalt and iron catalyst research. We have altogether 16 CSTR, 1 liter CSTR reactors and 3 fixed bed reactors. And also we have the capability of doing supercritical Fischer-Tropsch synthesis study and isotopic tracer study for carbon-14 isotopic tracer study for the mechanisms and so on. Also, we have the state-of-art analysis capacity to do the gas analysis for the permanent gas analysis and hydrocarbons. We use new HPGC can make the analysis in 3 minutes, and also we are capable of doing the oil and wax analysis up to carbon number 40, and we are developing, we actually now can do the analysis for the water phase products like alcohols and acids and etc. oxygenates in the water phase, and oil phase for the wax phase oxygenate analysis. We are developing the technology. Hopefully we can do it in the near future. The Fischer-Tropsch synthesis catalyst down to cobalt and iron. The choices are down to cobalt and iron catalysts for the commercialization usage. For the nickel and ruthenium catalyst, I won't talk too much about that there. I just outlined a figure, outlined a table about people's common perceptions of catalyst comparison of cobalt iron catalyst. For the some are actually all these perceptions. Some are right, some are not so right. Especially under the different conditions you're considering. Let me just go through the list. First, you say the chain growth probability. The common concept is cobalt have higher alpha value, and iron have lower alpha value, which actually, for the unpromoted iron catalyst, yes, the alpha value is lower than cobalt catalyst, but with potassium promoted and catalyst, and the alpha value for actually Celsius commercialized Fischer-Tropsch slurry phase reaction, the alpha value is about 0.95. Actually higher than the conventional cobalt catalyst, because unless you do the eggshell preparation for the cobalt catalyst, the generally alpha value for the cobalt catalyst is around 0.8 to 2.9. And for the activity, the concept is that cobalt has higher activity than iron catalyst. It's true only that if you don't consider this low stability. Yes, if you want to run a cobalt catalyst as a high conversion, you can run as high as 95% conversion, but then the stability won't be to your favor. So, but for iron catalyst, actually. If you adjust the promoters and the space velocity, you can run also very high activity as much as 80%. Which actually, so the comparison people's concept have, it all depends on what kind of conversion level you want to maintain, and how much stability and the feed gas composition you are considering. For the olefin selectivity, this is quite true. There's no doubt about it. For cobalt catalyst, you have low olefin selectivity. For iron catalyst, you have high olefin selectivity. And the feed gas ratio for cobalt, basically you are fixed at 2.0 or around there. But for iron catalyst, you can operate in a wider range. So that's works to the advantage of if you have coal-based syngas. For the water gas shift reactions, definitely cobalt is not so active for water gas shift reaction, and iron is very, very active. And for the methane selectivity, cobalt has higher methane selectivity than iron catalyst. But when you think about it, all the actually products you can use is the CO2 and methane and plus together and C2 to C4 paraffin. But when you combine the CO2 selectivity and methane selectivity, actually altogether cobalt still works to your favor, because that CO2 selectivity for iron is much higher for cobalt, while the cobalt selectivity for methane is just slightly, actually not too slightly, but higher than iron catalyst. But altogether, CO2 selectivity plus methane selectivity, cobalt is still lower than iron catalyst. And the temperature range for iron catalyst, you can operate it either at low or high temperature, which you can anywhere from 230 to 270, 320. You can go 300 or higher in a fluidized reactor. And for cobalt, you can only operate at low temperature, because if you go higher temperature, then the selectivity goes to methane. You won't get too much C5+ hydrocarbon products. And for the temperature sensitivity for cobalt is very sensitive to the temperature. If you 0 degrees higher, then you get different selectivity, and also the deactivation of the catalyst is faster, so you won't get stable catalyst, and selectivity is not working as your favor. But for the iron catalyst, not so sensitive to temperature changes, and also for the sulfur tolerance, cobalt is very sensitive to sulfur poisoning, so you have to have real clean feed gas for cobalt catalyst. Iron, you also need to do the desulfurization, but not as much sensitive as cobalt catalyst. For the stability and the lifetime, the common concept is that cobalt's lifetime is longer than iron, but then you have to have optimized preparation and operation conditions. Not too many commercial companies they really can maintain that supports the cobalt's stability. Actually, a lot of patents are actually concerning about the regeneration and both in situ and ex situ regeneration of the cobalt catalyst. Means that actually you can't maintain activity at desired level for cobalt catalyst in commercialized reactor. Not you can't. It's difficult. You have to optimize your only CSR now they claim that they can operate it in a very stable conversion for a longer period of time. And the cost for cobalt is high and for iron is low. And for the iron catalyst, the major problem for the slurry phase reaction is the separation of the catalyst from the wax products. If you actually, because it's the robustness of the catalyst, because cobalt is a supportive catalyst, so the velocity is good. And for iron catalyst, because it's a precipitate catalyst, so it has a possibility of breakage, so the separation will be difficult. Separation of the catalyst from wax will be difficult, but if you solve the separation problem, then the iron surface synthesis is more like a safer and low risk operation than cobalt. While cobalt, you have to have long period of stability because the cobalt is very expensive, and also you have to control the temperature very well, and you have to have a cleaner feed gas. But the general productivity for cobalt for the surface is higher than ours, so this is a trade-off between all these factors. So the comparison, the choice of iron or cobalt on commercialized or based process, I guess you need to consider mainly the feed gas composition, what kind of which is the source of your syngas feed, and also the current infrastructure you have and desired products and so on. So there's no clear-cut rules which one is the preferred catalyst. There have been, today I'm going to talk about iron catalyst. So mainly it's alkali-promoter effect. So the alkali-promoter effects mainly studied on the potassium promoters. Potassium promoters actually is reported to increase the alkaline selectivity, alkali selectivity, and it will give you a higher molecular weight products. And also, the research has been done on the activity of Fischer synthesis and water-gas shift reaction, and it says that potassium can increase the Fischer synthesis and also the water-gas shift activity. And the massive selectivity is lower for the promoter, for the potassium-promoted catalyst. Although alkali-promoter is very important for the iron catalyst Fischer synthesis, the study of the other promoters, other alkali promoters than potassium is not too commonly reported in the literature. The only papers we found are actually one paper was done on under atmospheric pressure, and the precursor of the catalyst of the iron designation of the nitric salt, and it has give you a low conversion level and not stable. And Dr. Mike Dry, he actually had a paper on fused iron catalyst promoted with different alkali promoters, and the conclusion is based on the fused iron catalyst, and he said that rubidium and potassium are the superior promoters than other group 1 alkalis. And the Sassos work actually were done under the hydrogen seal ratio of 3.2 and temperature of 290, and their pilot plant data was 320 degrees C and in a fluidized bed reactor. So actually, under the normal slurry phase reaction, the alkali promoter effects hasn't been widely investigated. So I think we need some updated research on this subject. And also, what we have done on this study is that we have done a wide range of space velocities, so we can compare the different promoters at the same CO conversion levels rather than change of the different conversion levels because of the effect of the alkali promoters. You will have a clearer concept if I show the figures. The experimental part of this study is that first I'll talk about some catalyst preparation. It's basically just a precipitation of the iron nitrate in ammonia, concentrated ammonia hydroxide, and the pH value is 9.5, and we stir the solution continuously. And TEOS was this one would. Yes, the TLS was the silica source. We add silica in this iron catalyst, and the catalyst was washed and filtered and dried and crushed before calcined at 350 degrees C. And the alkali-promoters were added by supervenous impregnation method. The precursors of the alkalis, the promoters are alkali carbonates, and these were added. The alkali promoters were added before the calcination. And the catalyst decomposition for the unpromoted iron is iron catalyst. Actually, we call it unpromoted. It's potassium promoted, alkali promoted. Actually, we already have silica, so it's 100% 100 iron and 4.6 silica. This is atomic ratio. And for the alkali promoted catalyst, we have all the same 100 iron and 4.6 silica, but we have 1.44 alkali metals from glycerin and sodium and potassium and rubidium and cesium. We compare all the promoters at the same atomic ratio level. These are the reaction conditions we used. We use 1 liter CSTR, and activation of the catalyst, we use CO at 270 degrees C at 175 psi. We activate the catalyst for 24 hours. And then the reaction condition is that the temperature is the same as 270 degrees C, and the hydrogen-CO ratio is 0.67. And the pressure is 175 psi also. The space, we vary the space velocity from 5.0 to 65 cm per gram of iron per hour to get the whole range of the CO conversion level. And we have the 3 traps. One is a 200 degrees C trap, one is a 100 degrees C trap, and one is 0 degrees C trap. We use online GC analysis to do the gas composition analysis. This is our basic CSTR setup. Our 16 CSTRs are all set up the similar kind of setting. Here you have a detailed look at the CSTR itself without the trap system. Here you have feed gas in. Normally, we can feed in different gases like CO2 or nitrogen, inert gas. And with CO and CO2, we have mostly we have 4 massive controllers can introduce 4 different reactants in, and through a dip tube, so you have dip tube down to the liquid level, and here's magnetic steering. So we normally operate it at steering speed of 750, and here's the inlet filter, in reactor filter here. So the overhead gas goes to the warm trap, which is controlled at 100 degrees C, and then connected to a 0 degrees C trap. And for the liquids, if the liquid level is above the filter level, we use the pressure difference to push the liquids out to the hot trap, which is operated under 200 degrees C. So we can take the liquids out and maintain the constant liquid level. We take the liquid out periodically, not continuously. And also, so this is, and also right now we have the capacity actually to take catalyst samples out in situ. We have a dip tube down here, so we can have a valve here, so we can take the catalyst out from the reactor under the inert gas protection, so we can do the in situ characterization of the catalyst. Do either for the iron catalyst we do multiple analysis, and for cobalt catalyst we do some other exams or TPR or any other catalyst characterization. So these are the diagram with the traps. You have we have another outside filter here. to separate the catalyst to prevent the catalyst going to the trap. So this is overhead. So we have it goes through the warm trap, and then it goes through 0-degree traps to further condense the lower boiling point region of the hydrocarbon products and water. And here we have 200-degree C trap to actually collect the liquid products from the CS2. Now the result of the different alkali promoters and ones that without alkali promoter, just iron and silica. You can see that just iron silicon itself, the deactivation. I forgot to mention what we did is that we changed the space velocity continuously, but we always, after a certain period of time, we always come back to the space velocity of 10 to check the deactivation rate for the catalyst. So we got the deactivation rate for each of the catalysts we studied. And also we use this deactivation rate to calculate back to make the correction of the conversion we got for the different space velocity data. Right now we got, see, it's a really beautiful trend. You can see that the N-promoted iron, that the N-promoted iron catalyst, the deactivation rate is the lowest. It has 0.21, and for lithium promoted it's 0.48% CO conversion per week. And for the sodium promoted is 0.84, for the potassium is 1.23, and for the rubidium is 1.8, and for the cesium is 2.75. So you can see that the more basic the alkali promoter is, the higher the deactivation rate is. Here we come to the most important figure here is the CO conversion as a function of space-time. Because we changed the space velocity here, so we got the different conversion, we got the conversion level for different catalysts under one space-time, which is actually space velocity. You can see that you have potassium, which is this pink curve. It got the highest activity, both at the low conversion level and actually both at the high space velocity and low space velocity. And you have sodium on this red one, and this actually have the second highest under high space velocity, but the third highest under the low space velocity. For the N-promoted alkalis, unfortunately, we didn't do the low space velocity run here. We stopped it at 10. But you can see that for the conversion level, medium and low conversion level, you can see the change is that potassium is more active than sodium promoted and then N-promoted, and for the lithium and rubidium and cesium promoted ones, actually activity is less than the N-promoted ones. See, if it's a cobalt catalyst, then it's pretty simple. You say, okay, so this is more active. Potassium is the most active, and sodium is the second most active for the low conversion levels, and for the rubidium promoted for the high conversion levels, which is the low space velocity, it's the second highest active ones. Then you see it's pretty simple, but for the iron catalyst, don't forget you have water gas shift reaction. So CO conversion are two parts. One is water gas shift reaction, one is Philip-Tropsch reaction. So you have to distinguish between these two parts, which one is has more water gas shift activity than the other one. I guess, right now what we mainly concern is the hydrocarbon production rate, which one can give us more hydrocarbons, these products we desire. So when you say this is actually probably a bad point, but when you see the trend is like potassium, yes, and sodium, and the unpromoted one actually gave, at a reasonable space velocity gives higher, the similar kind of change as the CO conversion level. You have the highest hydrocarbon production rate for potassium, and the sodium is the second, and the unpromoted is the third, and then all the others are pretty close to each other. So this is the water gas shift rate as a function of space-time. When you look at it, it's a very interesting trend. You can see that basically it goes through a maximum, the unpromoted one, because we didn't go too low. So here we missed some point. You can see that all this goes to a maximum and then decrease. And you see that for the unpromoted ones, the maximum is at the lowest space-time, which is the highest space velocity. And then you have the lithium promoted one, then you have the sodium promoted one, then you have potassium, and for the rubidium and the cesium promoted ones, the maximum is much further down on the space-time, which is much higher the space-time, which is much lower the space velocity. So this change, water gas shift rate trade, is very beautifully trended as the basicity of the promoters. For the water partial pressure figures, you can see also that it goes to a maximum, then goes down. And for the lithium promoted catalyst, it has the highest water partial pressure, means that the lowest water gas shift activity. Carbon dioxide partial pressure always increase with space-time, which means the decrease of the space velocity. So that's the change we can expect. This water gas shift quotient, which is actually the calculation equation, is the partial pressure of CO2 times partial pressure of hydrogen divided by partial pressure of water, partial pressure of CO. You can see at low conversion level, these are all similar to each other, but with higher conversion level, potassium to increase drastically. Higher, and for the lithium one is is the lowest one, so it has the lowest water gas shift reaction quotient, and potassium has the highest one at higher conversion level. See. Fraction of CO converted to produce hydrocarbons, so that's the fraction. Actually it's actually the rate of CO divided by the rate of phytotropism divided by rate of the total rate. So you can see that because that phytotrops reaction is generally must be higher than the water gas shift reaction rate. So this must be higher than 0.5. So you can see that the potassium promoted when it has the lowest fraction of CO converted to hydrocarbons. It's basically what happens is that you have higher CO conversion, but not as much CO has been converted to hydrocarbons. A lot of them has been converted to CO2, and for the others are pretty close to each other for this curve. Here it comes down to the selectivity other than the water gas shift, like CO2 selectivity. We come down to the methane selectivity and the olefin selectivity. You can see that With unpromoted when it has the highest massive selectivity, and then you have glycerin, and then you have sodium and potassium and so on. So its trend is that the more basic the alkali promoter is, the lower the massive selectivity would be. And the same trend for the olefin selectivity. Here's the C2 alkaline selectivity. This is C2 olefin divided by C2 paraffin plus C2 olefin. You can see that for the unpromoted one has the least olefin, and then the glycerin, and then the sodium, and then potassium, and so on.
Are you reaching the conclusions?
Yes. The conclusion of this study is that, you want to see the conclusion then? The addition of alkali promoters to alkalis increase the olefin selectivity and decrease the massive selectivity. The more basic the alkali was, the higher the olefin selectivity, the lower the massive selectivity. As far as the hydrocarbon production rate is concerned, the rating of the alkali promoters are the potassium is better than sodium, better than promoted, better than glycerin, and rubidium and cesium are the same. And this is contradict to the the previous conclusion that rubidium are the best alkali promoters, and potassium is the second. And the more basic the alkali promoter is, the higher the deactivation would be. And we have